So let's try vertical forces lesson. So one type of vertical force question is an elevator problem. And elevator problems aren't too bad because there's only ever two forces acting on an elevator with this setup that we have in physics. So they're on Earth, they're close to the surface of the Earth. So all of these elevators are going to experience a force of gravity. And if it's just an empty elevator in each situation, the force of gravity on all three should be exactly the same. So the other force acting on the elevator, because it's not resting on the ground, is this cable here. So in this cable, the force of tension could be smaller. The force of tension could be the same size, or the force of tension could be bigger. Those are the three scenarios that we could have. And depending on which of these scenarios is happening, it affects how the elevator moves, right? So in this situation, if I draw on a little vector diagram here, my net force is towards the bottom because Fg is bigger than Ft. So if my net force is towards the bottom, my acceleration is down in this situation. But my velocity could be either up or down. So if my velocity is up, well, velocity and acceleration are in the same direction. So if it's moving up, that means that it's slowing down. And if my velocity is in the opposite direction, if it's moving down, then these are in the same direction, so it's speeding up. Okay. If these are the same, it means Fg is equal to Ft, which means that we'd have an F net that's equal to 0. And anytime we have an F net equal to 0, it could be stopped, or it could be moving at a constant speed. The other scenario is when Ft is bigger. So if I draw a little vector diagram here, if Ft is bigger than Fg, that means our net force is up, which means our acceleration is up. So if my elevator is moving up with its acceleration up, it's going to be speeding up. So if it's up, it's speeding up. And if my velocity vector arrow is down, and they're in opposite directions, if it's moving down, and this is my free body diagram, that means that it slows down. Right, so 6 different scenarios here. Well, it's technically 7 because this could be moving at constant speed up or down. So 7 scenarios, but just 3 different free body diagrams for all those scenarios. So we're going to use these free body diagrams to help us out and solve these elevator questions. So you need to know what the term apparent weight means. So a person standing on a scale, just like a regular bathroom scale, a weigh scale in an elevator, will see the scale reading change as the elevator is accelerating. This is because there's different forces acting on it than normal. Normally you just have normal and gravity and it takes the reading from that, but now you have this force of tension that makes things different and they can be bigger or smaller than the other one. So the person can feel heavier, lighter, or the same as their normal weight, depending on what the elevator is doing. So to find out if they feel heavier or lighter, what we need to do is we need to find the force of tension in that rope. That force of tension will tell us what their apparent weight is, depending on what that elevator is doing. Okay, so let's try a question like that. So we have a 50 kilogram, or it also gives the weight of the woman here, right? So Fg equals mg. So to find this weight, all that this question is doing is it's going 50 times 9.81. So this is a weight, this is a mass. So the 50 kilogram woman is on a high speed elevator. Find her apparent weight if the elevator is accelerating upwards at 5 meters per second, moving at a constant velocity of 10 meters per second, and accelerating down at 5 meters per second. So these are the 3 things that we're going to look at. So let's switch to this screen. So let's look at this first scenario where the elevator is accelerating upwards at 5 meters per second. So we have to draw the correct free body diagram. And if we want it to be accelerating upwards, let's draw FG in here, we need the net force to be upwards as well. So our force of tension is going to be bigger. Let me just make it noticeably bigger. Our force of tension is going to be bigger than our force of gravity. If it's accelerating up, this will give us our net force up, which means acceleration up. And then if our velocity is up, then it's going to be accelerating, it's going to be going faster upwards. So we can write an F net equation for this. F net, I'm going to make up positive, down negative, force of tension minus force of gravity. Okay, so what you need to know when doing these is this is the lady's normal weight. What this is this is her apparent weight. And that's what we want to find. How heavy does she feel in this situation? So what we need to do is we need to rearrange the equation to solve for Ft. So I'm going to add an Fg to both sides, and I get F net plus Fg is equal to force of tension. I can break this down into Ma. And normally I could break this down into Fg, but they already gave it to, or Mg, they already gave it to us in the question. So I'm just going to keep it like that, and we'll solve for Ft. So the mass of the woman is 50 kilograms. She's accelerating upwards at 5 meters per second squared. And then we're going to add on that 490.5 newtons. That's the weight they gave us in the question. That's her normal weight. And we can solve for how heavy she feels. So 50 times 5 plus 490.5. So she feels 740.5 newtons. So this is how heavy she feels. So this is her normal weight. This is her apparent weight, so she feels heavier. So what she's going to experience during this elevator ride is her knees are going to buckle a little bit. If you've ever had that feeling, that's because you feel a little bit heavier than you normally would. Okay. The second scenario is moving up at a constant velocity. So I'm going to draw on. So if we're moving at a constant velocity, that means that Fg and Ft are the same size. Oops, this is Ft. So if Fg is equal to Ft, and this is her apparent weight, this is her normal weight, and her normal weight is 490.5 newtons, well, this is going to be 490.5 newtons, and she feels exactly the same. If you're moving at a constant velocity, you don't feel any different, so she feels her normal weight. So this last one that we're going to focus on is when she's accelerating moving down, right? So for her to be accelerating moving down, right, her velocity's got to be down, and her acceleration would have to be downwards as well. So she's accelerating moving down. And if we want our acceleration to be downwards, we need our F net to be downwards. So that means that our Ft should be smaller than our Fg in this situation. Okay. Because she's accelerating downwards, I'm going to make down positive. You should always try to make positive the direction of your acceleration. So I'm going to make down positive because that's the direction of my acceleration. So when I write my F net equation, I end up getting that Fg is positive and Ft is negative. We're trying to solve for her apparent weight. So what we can do is we can subtract an Fg from both sides, and we get F net minus Fg equals, and this negative sticks around, negative Ft. But I don't want to find a negative version of the answer, so the quickest way to get rid of this negative is just switch the signs of everything. This is positive, so I make it negative. This is negative, so I make it positive. This is negative, so I make it positive. So I get negative Ma plus Fg is equal to my force of tension. Okay, so negative 50 kilograms times the acceleration, which is moving 5 meters per second downwards, 5 meters per second squared downwards, and we said down is positive, so this negative should actually be outside the brackets like that. and then her normal weight is 490.5 newtons. So if I plug that into my calculator, what I do is I know I want to get that mass times acceleration negative, so I'm going to go 50 times 5, and then I'm going to just multiply my -1. So I'm going to make sure that it gets nice and negative, and then add on the 490.5, and I get 240.5. So her normal weight is 490.5, she feels 240.5, so her apparent weight is lighter, right? And we also said that your apparent weight is equal to your force of tension, and if you want to know if it's going to be bigger or smaller, well, this is normal weight, this is apparent weight, so just looking at the free body diagram, yeah, the apparent weight should be bigger. Ft is smaller than Fg, normal weight, apparent weight. Well, it makes sense that it's smaller. So we can just look at the free body diagram and figure out if she's going to feel heavier or if she's going to feel lighter in those scenarios. Atwood machines are one of the trickier things that we do all year. Atwood machine problems involve changes in direction of force through tension in a rope, storing across a pulley, so it looks like this. So to analyze what happens here, let's draw a free body diagram of the forces acting on both mass 1 and mass 2. Okay, so we're going to assume to start off that we have a frictionless table, or that these wheels are frictionless enough that it's fine. So yeah, let me switch my screens. So we have mass 1, my pulley, mass 2. So the forces acting on mass 1, obviously there is a force of gravity and a force normal. Sorry, that's a little bit off the screen, but you'll just have to trust me that those are the same size. And what propels this forward is there's a force of tension from mass 1. So we're going to call these all mass 1. Okay, mass 2 has a force of gravity like that, and it also has a force of tension like that. So this one's kind of like an elevator. So these are the forces acting on my Atwood pulley. Let me just adjust that. There we go. Now we can see all of them there. Okay, and because we don't have any friction, we'll assume that it's frictionless, so we'll leave that out. So we drew a free body diagram. So what we can do to make this simpler is we can straighten it out. So these problems can be simplified by straightening out the rope and laying the whole apparatus along the horizontal. So instead of pretending that mass 2 is dangling there, we'll pretend it's up here like this. But it's important when you straighten this out that you don't switch the direction of the forces. I'll show you, I'll straighten it out and I'll show you that. It's also important to remember that while only cart 1's weight is doing the pulling, or I should say cart 2's weight is doing the pulling, the total mass of all the cars must be considered when calculating the acceleration. Well, only one car, only one car, so that is right. So what we're going to do is we're going to take this and we're just going to lift it up there. So it's like mass 2 like that. So when I do that, this force of gravity 2 and this force of tension 2, you can see how they sort of stay in the same direction. And now, when I analyze this, right, I can, everything is sort of in the same direction a little bit better. And I have force of tension 1, force of tension 2. If it's the same rope, the magnitude of the tensions have to be the same. So that means that these cancel out. And that this, I know it cancels out with this. So what I'm left with is I'm left with one force. Okay. So let's do an example with this same situation. So we'll throw in some numbers now. An Atwood machine is connected as diagrammed below. Given that mass 1 is 500 grams and mass 2 is 1 kilogram, assume the surface is frictionless. What is the magnitude of the acceleration of mass 1 and mass 2? Okay, so we already drew it out, but they've just given us some numbers. So they said that mass 1 is half a kilogram, and this one is 1 kilogram. So what we need to do is we need to write an FNet equation for this. So FNet is just going to be equal to this cancels out, this cancels out, this cancels out, this cancels out, just FG2. That's it. That's all that's left over when everything cancels out. So what's important to understand when doing this is this side over here is which mass makes it accelerate, and over here is which masses accelerate. That's what we need to ask ourselves with both these sides. So which mass makes it accelerate? Well, FG1 doesn't make it accelerate because it cancels out with the force normal. So it's just mass 2 times gravity that makes it accelerate. Which masses accelerate? Well, yeah, this one accelerates, but these are attached by a rope. So this accelerates too. So when we break it up into mass times acceleration, we need to add the masses together because both masses accelerate. So if we're solving for our acceleration, we can move mass 1 and mass 2 down here, and we can find our acceleration. So mass 2 is 1 kilogram times 9.81 meters per second squared. And mass 2 is half a kilogram and 1 kilogram. So I plug this all into my calculator. 1 times 9.81, it's pretty obvious what that's going to be, divided by 1/2 plus 1. So both of those masses accelerate, and we get our acceleration to be 6.54 meters per second squared. They're attached by a rope, so they're going to have the same acceleration, and that's how we do this question. So there's a second part to this question. It says, what is the force of tension in the rope? So we can't look at this mass 1, mass 2 system together if we want to find the tension in the rope, because no matter how we do it, that tension in the rope cancels out. So what we can do to figure out the tension in the rope is we can look at them individually. So I have mass 1 here. So our 0.5 kilogram mass 1 here, and it experiences a force of tension, force normal, force of gravity, like that. And then we have mass 2, which is our 1 kilogram mass. It experiences a force of gravity and a force of tension. And my force of tension would be a little bit smaller because it's accelerating downwards. So I want to look at the forces in the direction of motion. So I can write an FNet equation for this, where FNet is equal to the force of tension. So if I want to find the force of tension, I just have to go mass times acceleration. Well, I would go 0.5 kilograms times my acceleration that we just found, 6.54 meters per second squared. And if I do that, I can find my force of tension in my rope. So 0.5 times, that's 6.54. And I get my force of tension to be 3.27 newtons. So that's the easier way of doing this. I can also do it with this one as well. It's just a little bit harder. So it's accelerating down, so I'm going to make down positive, up negative. And I can write an FNet equation where it's Fg minus Ft. I want to find force of tension, so I subtract an Fg from both sides. Fnet minus Fg equals negative force of tension. Make this negative, this positive. Right, and it's the same as that question, that last elevator question we did. Negative mass times acceleration, plus I'm going to break this down into mg, is equal to my force of tension. So negative 1 times 9.81 meters per second squared, so that's a kilogram, plus 1 kilogram times, this acceleration is not, this is 9.81 meters per second squared. This is 6.54 meters per second squared, because that's our acceleration. Okay, and if we plug that in, we should get the exact same answer. It's just a little bit harder of a way of doing the same thing. So if I go, I'm just going to go 1 times 6.54 I'm going to make sure that's negative, so I'm going to multiply it by -1, and then I'm going to add on 1 times 9.81, and I get 3.27. Right? Both give me the same answer. They cancel out as a whole, but if I look at them separately, I can find out that force of tension. So there's one more type of Atwood-Pulley type question that we could answer. So given the same masses as before, if we set them up like this, calculate the magnitude of the acceleration of the two masses below, and assuming they both start from rest, what's their maximum speed reached? Okay, let's do that. So you start it the same way. Any of these Atwood-Pulley type questions, you start the same way. We have, let me put my camera back to where it was. Here we go. So you have the two masses. We have our 1 kilogram mass, and then we have our 0.5 kilogram mass. Yeah, and we can draw a free body diagram, right? So both of them experience a force of gravity. So we're going to call this Fg1, and this is Fg2. And both experience a force of tension, Ft1, and we'll call it Ft2. So this is kind of confusing the way that it is. So what we can do is we can straighten this out. So we can put mass 1 up like this, and then we have Fg2, Ft2, and then also straighten this one out. This is mass 2. Well, that's a 1 kilogram mass, that's why I have 1 there, and then 0.5 kilograms. So this is Fg1, and this is Ft1, like that. So we straightened it out. Okay, now when it's straightened out, our force of tensions are always the same, so they'll cancel out. Well, does my Fg's cancel out? And the answer is no, because this is 1, this is 0.5, so this is a bigger force of gravity. So when we write our Fnet equation, Fnet's going to be equal to, I'm going to make this way positive because it's going to accelerate that way, Fg2 minus Fg1. Okay, so remember that on this side, it's which masses accelerate. Well, they both accelerate, so we need to go mass 1 and mass 2 times acceleration. This one is mg, but we're talking about mass 2. And this one is Fg equals mg, but we're talking about mass 1. Sorry, all my pens are dying here. A new pen. Okay, and if we're trying to find the acceleration, we just have to move mass 1 and mass 2 down here, and we can solve for our acceleration. So mass 2 is 1 kilogram. G is 9.81 meters per second squared. Mass 1 is half a kilogram times 9.81 meters per second squared. And then mass 1 is half a kilogram, and we add it to 1 kilogram, and we can find our acceleration. Oops. So on top, I'm going to go 1 times 9.81 minus half times 9.81. That's my top, and then divided by my bottom, which is 0.5 times 1. Oops, plus 1, not times 1. And I get my acceleration of my system to be 3.27 meters per second squared. Okay. The second part of the question is asking how fast are they going to be going when they reach their top speed. So we just have to, if we want to find speed, we can use VI VF DAT. And we know our acceleration is 3.27 meters per second squared. We can assume they stop from 1, and in the picture it shows that they drop a distance of 1 meter. So if we want to find our final speed, we want one without time in it. So we're going to use VF squared equals VI squared plus 2AD. We're trying to find our final velocity. This is 0, so we can get rid of it and square root both sides. So if we just go 2 times 3.27 meters per second squared times our distance of 1 meter and square root it, we can find the final speed. And even though they have different masses, they are attached by a rope, so they have to be going the same speed. So 2 times 3.27 times 1. And then I'll square root my answer. And this is their final speed. So we have 2 sig digs in the question, so their final speed is 2.6 meters per second. So let's do a board question. So try this out on your own, pause this video and see if you can get it. Herman is tied to a 500 kilogram mass and is being accelerated towards the edge of the cliff at 8.6 meters per second squared. What is Herman's mass? Kind of a messed up question, but Herman survives and is unharmed in this physics question. Okay, so this is an Atwood-Pulley question. We have Herman, which we'll call mass 1, which we don't know. And then we have mass 2, which is 500 kilograms. And that's what we want to find. So we draw our free body diagram. This is FG2, force of tension 1, force of tension 2, force of tension 1, force normal, and force of gravity. It says it's frictionless, so he has no hope of survival. Just kidding, he's fine. So this is my 500 kilogram mass. When we straighten it out, FG2 goes up here, FT2 goes here. So this will cancel out with this will cancel out with this, and we get our F net to just equal FG2, just like the one we did. We have to rearrange it different. So both masses accelerate. So it's mass 1 plus mass 2 times acceleration. And Fg breaks down into mg, but we're talking about mass 2. So we want to find out mass 1. So if we want to find out mass 1, we just have to rearrange it by throwing acceleration down there and subtracting a mass 2 from both sides. And we get mass 1 is equal to this. So mass 2 is 500 kilograms times 9.81 meters per second squared. The acceleration is 8.6 meters per second squared, which is a big acceleration, and we minus it by 500 kilograms, and we can get our answer. So to type this into my calculator properly, I'm going to double bracket it to start. I'll do it all in one. 500 times 9.81, and then divided by 8.6. Close my other bracket, and then I'll subtract 500 from that whole thing. And we get Herman's mass to be, we have 3 sig digs, 70.3 kilograms. Okay. So one last thing that we need to talk about is assumptions. So assumptions is a word that I'll use on a test. And usually what assumptions are is they're measurements in physics that exist, but they're so small that we can exclude them, okay? So it's kind of like when we were talking about acceleration due to gravity, we're talking about free fall. When I drop the ball, we can ignore the friction on it because it's heavy enough, it's aerodynamic enough, that would be an assumption that we could have. With the piece of paper, if we try to ignore the air resistance, well, we can't really, because that's not really an assumption. It's big enough that it affects the movement of it. So in this Atwood-Pulley question, what are some assumptions that we have? Well, it's things that we ignore. So things like friction. So there are other places where friction can be had, like the pulley. The pulley is, we say it's frictionless, but it does have a little bit of friction. But the fact that we make it a wheel means that, well, we can ignore that. It's probably going to be pretty small, right? There's also going to be friction between the table and the block. But again, if we put those on wheels, then it becomes an assumption because we can say it's small enough. There's also air resistance right here, right? There's air resistance on this 5 kilogram mass, but it's heavy enough and aerodynamic enough that we can say that there's not a ton of friction acting on it, right? So those are all assumptions. So when we talk about assumptions, that's what we would be doing. That's what I'm talking about. Things that are so small that it doesn't even matter. Even using 9.81 meters per second squared. It's not 9.81 everywhere in the world. Some places are a little bit closer to the center of the Earth, some places are a little bit further away, but it's going to be pretty close to 9.81 the whole time, and that's a big assumption. Like that's like an assumption that we don't have to worry about too much. So to finish this off, I just have a clip of Big Bang Theory that talks about assumptions. Leonard tells a joke and it talks about physics assumptions, because whenever we draw a free body diagram, it's always a spherical object in a vacuum with no friction, but it doesn't really work for real life problems. So here's a clip of that.
It's okay, just open with a joke, you'll be fine.
Okay, joke. Okay. How about this? There's this farmer, and he has these chickens, but they won't lay any eggs. So he calls a physicist to help. The physicist then does some calculations, and he says, I have a solution, but it only works with spherical chickens in a vacuum. Right?
Oh, sorry, I've heard it before.
Well, let's roll.
Okay.
Hey, nice suit.
It's a classic, right?
So this is your homework. So there's some questions like we did. These are standard of excellence questions. These are a little bit tricky. So if you can't get them, just talk to me or don't worry about them too much. But these are the basics that you got to know.